Hi there. This is Rebecca. I am going to be doing my final project on spatial analysis of Washington wildfires using R. So basically what I'll be doing is creating some visual maps to interpret some of the data and wildland fires in Washington. And then I'll go into some methods for analyzing spatial patterns and determining the locations of any of spatial clusters using point pattern analysis methods. I decided to investigate fires in Washington because they've increased in severity and frequency in the last few years. I've just noticed, living here all my life, every summer we have air advisory warnings, so it's been getting worse lately. Fires in the West Coast have become increasingly expensive and devastating. Often state resources are not enough to contain fires, so federal dollars are spent to address these issues. And in 2016, one of the final executive orders that Obama put in place was the fire risk assessment for federal facilities, so that steps can be taken to secure federal assets from threat of wildfires. So it is a large issue. So here's some of the libraries I'm going to be using for the analysis. Of course, I'm going to use XF for shapefiles, TMAP, and TMAP tools for making some maps, tinyverse for data wrangling, and then also I'm going to be using this package right here, spatstat, to do the different spatial analysis methods. So first, I am going to load the historical wildfire data, integrated information system. I'll post the link. Yeah, I'll get that loaded in. In this file. So we can just do str to get a little better understanding of what's in this file. Lots and lots of information from state information from U.S. states. And we also have some actually Canadian territories in here. So I'm going to want to limit this down to just Washington. How do I do it? How do I narrow it down to just fires in Washington state? So I will use dplyr to filter out this variable Washington state. And then scroll down here and you can see all the states for the fires are in Washington. I'll also want to load in a county boundary file for Washington that I got from the Washington geodata website. And 11, and then I'll look at it. I'll also be using So I'm going to want to plot these on top of each other. So of course I'm going to want to make sure that the coordinate reference system for each match. So how do I do that? How do I check them? And how do I make them line up to the same coordinate reference system? So I'll call stcrs on both of the files and see that their coordinate reference system is different. So to make it the same, use st transform to set the CRS of the wildfires shapefile to the CRS of the county boundaries. So the fires in this data set date back to 2014. So I wanted to plot the fires over the years. So I created some different files for each year. And then I'll use TMAP to plot the fires over the counties. So the first one I did was 2020 and 2014, just to do a quick comparison of what this looked like, a while ago versus what it looked like last year. So this is 2014. And just a quick glance shows us, yeah, it looks like there's definitely a lot more fires happening last year. How would I plot these side by side to do a little bit better comparison? So I don't have to scroll. I can use TMAP arrange and then do the side by side comparison. So we have 2014 and 2020. Lots of fires, lots more clustered up. So how do we just quickly confirm how many wildfires are there were each year, if they are indeed increasing from year to year? We can use in row to count up the number of fires in each file. So 2014 we had 827. 2015 jumped up quite a bit, but then every year since it's been increasing as well. To the point where last year we had pretty much double what we had in 2014. So to see kind of how this changes over the years, wanted to get some idea of what this looks like over the years using a map. So first we'll join these together on the geometry. So the counties file, like the wildfires file. Then I'll set some breaks so that they're all standard in each map. Then I'll make these maps here for each year. I'll use the same breaks. And finally, I'll create a legend that has the information so you can kind of look at these. So something that's interesting that's happening, we are seeing more counties with more and more fires, and they are moving west, over the years. In these first few years, we didn't really have any on the western side, or we had some, but smaller amounts on the western side. Now we're seeing a much larger increase in the number of wildfires happening over here on the west side of the state. So now we'll move on to our point pattern analysis to see, are these occurring randomly in some areas, or is there kind of some pattern to them? I'm going to go to my R here just to see this a little better. So I'm going to look at 2017 data for the wildfires. And in some of these counties, it's pretty easy to see, clustered patterns, like here in Yakima. Here, it's not quite as clustered, but you can see it's spread out. But I was interested in looking at Stevens County, which is here, because it doesn't seem to have quite as clear of a pattern, and the points are a bit more, spread out. But as you saw above, this has been one of the areas that consistently gets a high number of wildfires each year. So first I'll kind of isolate the county and the number of fires there. And then we'll do some spatial analysis. So I'll go back to now here. So to do some spatial analysis with spatstat, we need to do a few things, like create this window. And we'll need to convert our shapefile to a point pattern object for this analysis because it won't accept our shapefile. So that's because it contains its own file, its own data type. So that's what we do here, and then plot the fires over that window. So one of the questions we want to proposing with this spatial analysis is, are fires in Stevens County in 2017 randomly exhibit some kind of distributional cluster pattern? So that's basically the goal. So one of the things we'll look at is kernel density estimation. So one way to summarize the point there is to plot the density of points around a window called the kernel. The size and shape of the kernel affects the density pattern produced. So there's a very easy to produce kernel density estimation map for a PVP object using the density function from spatstat. This sigma value is basically a radius of the kernel. So right now it's set to 500 in the units of the CRS of the county file, which is meters. So right now we're pretty much just looking at individual fires. So that might not be big enough radius. So we can set that to 10,000. And we actually start to see clustering some of the patterns. So, all right. Then we'll move on to some quadrant analysis. So we're interested in knowing essentially whether the distribution of the points in our study area differs from complete spatial randomness. So the most basic test of complete spatial randomness is a quadrant test. And so we can carry out a simple quadrant analysis on our data using quad count. And this is part of the spatstat package. It's useful for starting to understand the Poisson distribution. Yeah, so we have the counts of each of the fires in each of these quadrants in this 6x6 grid that we overlaid over our window. In our case, basically, we want to know whether or not there's some kind of spatial patterning associated with fires in Stevens County. So we have to compare observed distribution points with a statistically likely complete spatial random distribution based on Poisson distribution. So these are the actual observed counts. So we're going to do some work to figure out what would be the counts if this was completely spatially random, and basically figure out, is it spatially random or is it is there clustering or patterning? So we'll turn those quad counts that we got into a table. And then to continue with the analysis, we need to make sure all of those values are integers. Check, they are integers, that's good. And then basically we'll calculate the sums from this table, sums, and calculate lambda, which is the value of quadrants. So now we're going to calculate what the expected value would be using the Poisson formula. So what the Poisson distribution is basically a probability in statistics theory. That is a discrete probability distribution that expresses a probability of a given number of events in a fixed interval of time or space if these events occur within a constant mean independently of the time since the last event. So this essentially is that Poisson formula. And this lambda being mean, this is one of those quadrant counts. This is E. And so this is the output of this is supposed to be this expected, what we would expect if it was supposed to be random. And then we're going to plot what our expectation is versus what our actual counts are. And we'll see if that follows a Poisson distribution. And here's what, plotting the expected in blue and the actual is in red. So typically a Poisson distribution would be, higher at these lower frequencies and, lower towards the end, and that's not quite what's happening. So we could say for the grid that we made, it appears that there's some patterning, and we can use different counts for the grid. I use a 6x6. It's different values. So we can do this another chi-squared test to see if we're seeing some patterning or not. So what we are doing here, it might be a little bit harder to see, but basically the spatstat package allows us to do a quadrant test and compare the expected values to actual values in a way, and it'll show basically the different values it expects. If it's statistically significant, the difference. This makes it a little bit easier to see. As I said before, I did a 6x6 grid. So each of these grids, or each of these quadrants has three numbers. This one is the expected. This one is this one is the actual. This is expected. And this is that p-value. That chi-squared test. And basically, if the p-value is less than 0.05, that means it's very, it basically means that we can, accept the hypothesis, or which is that there is some patterning or some clustering of data here. So obviously, this is a really empty region. This one has more distribution, but you see that some of these quadrants have a really low p-value, which means there's some kind of patterning. It would appear that there's some kind of pattern happening like this. Another Way to look at this is Ripley's K, which is a little bit easier than that chi-squared test, which was a little difficult for me simply because of the overlapping. And it's another way to compare the Poisson random model with a whole different range of distance radii. So this is what the Ripley's K function computes. And we can conduct a test again with spatstat. So basically this red line is the expected value, and this black line is the estimated values of the accounting for the effective edge of the survey area. So pretty much the observed way. So where the value of K falls above the line, the data appear to be clustered at that distance. So between 0 to about 1800, that's kind of clustering. We might see some clustering happening. Beyond that, at about 18,500, 19,000, we're seeing more spaced out. So basically, that's we kind of get a sense of what distance is clustered and what distance is spaced. That's kind of what this tells us. So that was kind of useful for telling us some exploratory things if we have spatial clustering present in our data. But it doesn't really tell us exactly where. I mean, we can kind of see with the quadrants, but this gets a little bit more specific. So to discover exactly, get a better sense of where the clustering is happening, we need to use a different technique. So one of the more popular techniques for discovering clusters in space, this physical space or variable space, is dbScan. It's a data clustering algorithm, and it essentially says that given a set of points in some space, it groups together those points that are closely packed together, points within so many nearby neighbors, marking as outliers points that lie alone in low density regions. Neighbors are too far away. So dbScan is one of the most common clustering algorithms and is also cited a lot in scientific literature. So it does require two values, essentially a kind of radius that we looked at back with that Ripley's K, and a minimum number of points. So basically we see a big bulge here around 1200. So that might be a good place to set as the radius. So that's what I chose for the CPS value. And then we can plot the results. So these colored points are, some of those clusters we see happening. And this is the outline of Stevens County. It doesn't look great, a little bit hard to tell exactly what's going on. So that wasn't very nice. So can we look at this some other way? So let's look again at this DB object that we just created. And it has cluster information in it. And we'll add that back into our points file. We'll create some convex holes, which will link those clusters together. And since 0 is in a cluster, we'll ignore that. All right, so let's plot this using ggplot. So this looks a little bit better. I don't really have a sense of where this is in space. I don't know if this is, I'm not quite sure what this is itself. So we can create another plot, maybe with a base map, because we have an idea of where this is in space. So I can use OpenStreetMaps. I actually went to OpenStreetMaps to get these the boundary points for the county. There are other ways you can do this with like BBbox. And then use this OpenStreetMap to plot as the base, and then plot the points and the convex holes over it. So that way we can see kind of some of the clustering that is happening in Stevens County. Now I would assume that there's clustering of fires for a lot of reasons, but here, you know, one of the obviously the fires is that, you know, when they're in one place, one can blow in another. So I would assume that's why we don't, you know, one place spark other ones. And this county is very rural, so yeah. All right, so that is for my presentation on spatial analysis, wildfires in Washington.